this video, we will talk all about the creativity of large language models, and there are 3 parameters I want to tell you about. They are a set of parameters that control the randomness of the output from large language models during the inference time. If you've used LLMs in playgrounds such as on the Hugging Face website, you might have been presented with controls like these to adjust how the LLM behaves. So today, we will explore temperature, top K, and top P. These are not the parameters the model learns during training. Instead, they are levers you, the user, can adjust at inference time to influence the model's output. Before diving into these parameters, it's essential to understand the Softmax function, a foundational piece in our discussion today. Here, we can see the architecture of transformer model. You see, the Softmax function really comes into play at the last step of the structure, ensuring that the final output from the transformer is clear probability distribution over potential class labels, making the decision process precise and interpretable. At its core, the Softmax function takes a vector z of raw scores for each token in its vocabulary output by the LLM, and transforms them into probability distributions over k classes. This probability is calculated through the following Softmax function, sigma. Okay, but don't get too scared of the math. To give a simple example, just imagine the LLM outputs a list of tokens, each with a raw score. The Softmax function will convert these scores into probabilities, such that higher scores translates to higher probabilities, and all the probabilities add up to 1. In this example, we only showed 3 words. However, the output from the transformer's softmax layer is a probability distribution across the entire dictionary of words that the model uses. For simplicity, the next examples of this video will also only show a few words. Now, where does temperature come into play? Temperature is a scaling factor applied directly within the softmax function, influencing the shape of the resulting probability distribution. Broadly speaking, the higher the temperature, the higher the randomness, and the lower the temperature, the lower the randomness. Let's examine the temperature-scaled softmax function, sigma. Notice that the temperature scalar parameter is applied to the original softmax function. We can have a few observations based on this. If temperature of T equals 1, it means no scaling, and we get a regular softmax function. If T is larger than 1, it makes the output probabilities closer to uniform, which means flatter, or more random. If T is between 0 and 1, it makes the output probabilities more extreme, which means sharper or more deterministic. I know this might still not be intuitive for some of you. Let's do a thought experiment. Imagine if T approaches to 0, then we will be dealing with extremely large exponentials, and the zi element with the largest value will dominate. That is, its probability will be close to 1, and all others will be close to 0. This would be equivalent to a greedy strategy, where the top probability token is always selected. Now, on the contrary, if T approaches to infinity, then the exponentials all become e to the 0 equals to 1. This turns the output into a uniform distribution. That is, all probabilities becomes 1 over n, which means all tokens are equally probable. This obviously isn't a useful model anymore. Different from temperature, top K and top P parameters does not change the shape of the probability distribution. Instead, they restrict the set of tokens from which the model can sample after obtaining the probabilities via the softmax function. Top K and top P both operate on probabilities by first organize them by descending order. Top K select the first K tokens to create a new distribution to sample from. For example, let's say we sampled using K equals 3 from this list of tokens. We will then only sample from the top 3 tokens that has the highest probability, which are apple, banana, and peach. Note that if K equals 1, then we get a greedy strategy again, where the most likely token is always picked. Top K is good if you want to introduce some randomness, but avoid highly improbable completions. Now, top P is similar to top K, but instead of picking a certain number of tokens, We sample the smallest number of tokens such that their cumulative probability is at least p. For example, let's say we sampled with a top p strategy using p equals 0.4. Again, from our example above, we will select the first 2 tokens to sample from as their probability adds up to 0.5, which is larger than 0.4. Top P is a slightly more adaptive method that offers a balance between randomness and determinism, irrespective of the size of the vocabulary. And if you want to avoid the rigidity of a fixed number like top K, often the best results come from experimenting and combining these parameters. For example, using a slight temperature adjustment with top P can strike a sweet spot between creativity and coherence. I hope this was helpful, and now go out there and kill it. Lastly, I want to give you a quick update. This video came out late because for the past few weeks, I have been moving and settling into a new space. For the first time in my life, I'm able to have a dedicated studio space. I'm currently still in the middle of setting up a filming space for higher quality videos and a small workshop. Because I don't have a car, the process has been pretty slow and complicated. I want to make more useful videos just like this one. So smash the like button, and until next time, happy learning.